This is Honors Algebra 2 Pre-Calc. We are starting 2.6, which is special functions. So we're going to address three basic kinds of functions in 2.6. Piecewise functions, which are the ones that we're probably going to spend the most time on. Absolute value function, which you've already seen a little bit, and then step functions, which honestly aren't going to happen, aren't going to be like a huge thing in your life or a huge thing in math, but we're going to introduce them and make sure you know what they are. So piecewise functions of the three are probably the one that are the most difficult and also will come up. Absolute value functions will also come up, but I think you're going to find that they're not as difficult. So, all right, a piecewise function, remember things in math are named either after a person or after some sort of description, right, of what they do, and piecewise function is definitely not named after Dr. Piecewise. It's piecewise because it is essentially piece by piece, right, like each piece behaves differently. So a piecewise function has different function rules, think of those as like actions or what to do, for different parts of its domain. Think of that as like times. So you actually see real ones daily. Example, your course schedule. Now, okay, we're living currently in a world where we don't have regular course schedules and we don't actually have regular schedules at all, and we're probably all watching this video in our pajamas while watching small children or pets or whatever, right? I get it. But in the real world, before all the crazy quarantine stuff, we had schedules. And so your schedule might look something like chemistry from 8 to 9 a.m., African American history from 9 to 10 a.m., English from 10 to 11 a.m., lunch from 11 a.m. to 12 p.m. Obviously, it's a very oversimplified schedule. Algebra from 12 p.m. to 2 p.m. because you're stuck with me for 2 periods, and art from 2 p.m. to 3 p.m. So these are your function rules, what to do. You go to chemistry, you go to African American history, you go to English, etc. And when to do it are the domain restrictions, right? So that's an example of you see things all the time where you do different things in different situations, whether it's actually like a schedule like this or whether it's just like code switching stuff where you behave differently around different people, right? Where you sound different around your mom or your dad or your grandma than you do around the principal or your teammates or your teacher or your best friend, right? We all know that we do different things at different times, and piecewise functions are just a mathy way of expressing that you are supposed to do different things at different times. So this is what a piecewise function looks like in like algebra 2 or in an algebra class, right? So we have a function like f of x, and then we have this big brace, right, like a squiggly bracket, but it's called a brace. And then we have a set of function rules, like actions that we are supposed to take, and then a list of when we are supposed to take those actions. So what we're going to do is we're going to talk about a couple things using this f of x that I wrote for you over there. We're going to talk about how to evaluate it, like if I asked you to find f of a number, what would it be? And then we're going to talk about how to sketch a graph of it, okay? So I'm going to erase all this stuff because I need some room, and I don't want to erase that piecewise function because it's a pain to have to generate it or remember what I wrote. Okay, so in example 1, what we're going to do is we're going to evaluate the function, right? And the function's over here because I'm lazy and okay. So in example 1, we're going to evaluate the function. So let's start with, we're going to do f of 0. We're going to do f of 1. We're going to do f of 3. We're going to do f of 4. We're going to do f of 6. And we're going to do f of 10. Cool. All right, so I picked 6 numbers, and we're going to plug those in for x. So here's the deal. If you get to school late because you had a doctor's appointment or the bus broke down or whatever, right, the first thing you do before you run to class is figure out what class period you're in, right? You either look at your watch or your phone, or you ask someone in the office and say, oh man, what period are we in, right? If you have to, anytime you're late to something or you don't know what time it is, you check and see, well, where am I supposed to be? And you go there. This is no different. The first thing you're going to do is you're going to look at what time it is. Well, the time they're telling me is 0. Then I'm going to go over to my rules and say, okay, which of these domain restrictions applies when I plug in 0? And it's the first rule. So what I'm going to do is I'm going to actually number these. I'm going to call this function 1, function 2, and function 3. They're all part of the same function, but it's easier to number them 1, 2, and 3. So rule 1, rule 2, rule 3. So because I'm plugging in x is 0, I look at the domain restrictions, and here's the thing. If it's a function, the x can only get plugged into one of them. Because if it's a function, then it has to pass the vertical line test. There has to be a unique, correct answer if I plug in the x, right? So I look and say, which one of these 3 rules applies for x is 0, and it's rule number 1, right? So I'm just going to put a little 1 here so I know it's rule 1. Then I go ahead and plug in 0 plus 2. I use rule 1 and only rule because 0 only uses rule 1. You don't simultaneously go to chemistry class and African American history class. You go to one or the other, right? If it's first period, you go to chemistry, and if it's second period, you go to African American history, and that's it, right? Okay, so then I look at the time x equals 1. Well, x equals 1 falls in the window between 0 and 3, so yet again, I'm going to use rule 1. So I'm going to plug in 1 plus 2 and get a 3, right? I then look at x equals 3. Now, 3 is tricky, okay? 3 is what I call a breakpoint, and this is totally a Hoganism, so I'm going to go ahead and warn you. Okay, so this is a Hoganism alert, okay? I call a breakpoint the x values where a piecewise function switches rules. Switches function rules. So usually in my class, not always, but we have a pretty good track team at ENS, so usually in my class, somebody's on the track team and somebody has run in a relay. It's harder teaching from home because my very old dog sleeping on the couch is not on the track team and does not run in a relay. He's a very old dog and he's sleeping on the couch. But if I'm in class, I say, is anyone on the track team, has anyone run a relay? And I ask, what's the hardest part of running a relay? And the hardest part is always the pass of the baton, right? Because you can be an excellent runner, but if you can't pass the baton to the next runner without dropping it, or if they can't grab it without dropping it, then you're pretty much done, right? So the same thing here. These breakpoints are the places where I could have an issue because it's the trickiest part of the relay, right? Function 1's carrying the baton. It's all good, running along. But then x equals 3 comes along, and function 1 has to pass the baton to function 2. Right? And then when we get to x is 6, function 2 is going to have to pass the baton to function 3. So in this particular problem, the breakpoints would be 3 and 6. So in this particular example, the things that I would call breakpoints are 3 and 6, because that's where I'm switching from one function to the next, right? So that said, when we get to plugging in x is 3, we have to stop and say, wait a second, 3 shows up in both of these. Which rule do I use? Well, the 3 in the first rule doesn't have an equal to, but the 3 in the second rule does. So I'm going to use the second rule, which means I'm now plugging in 3 into a function rule that literally just says the number 5. It says 5. It's a 5. It's a 5 when x is 3. It's a 5 when x is 4. It's a 5 when x is 5. It's a 5 when x is 3.2. It's just a 5. So there's nowhere to plug in, and it's just a 5. Which brings me to when x is 4. 4 falls in the window between 3 and 6, so I'm still using function rule number 2, and function rule number 2 was just right 5. But when I get to 6, 6 is one of those breakpoints. Well, I look, and 6 doesn't have an equal to at 2. It has the equal to at rule 3, right? Like, so 6 has the equal to at rule 3, so now I'm using rule 3, which means I'm going to plug into negative x plus 7, so negative 6 plus 7 is a 1, right? And then for my last rule, 10 definitely falls in the window where 10 is greater than or equal to 6. So I'm still using rule 3, right? And so that's going to be negative 10 plus 7, which is a negative 3. So that's how I evaluate a piecewise function. Now, what we're going to do is before we do, this is a little bit unusual, but before we do P1, we're going to go ahead and graph E1 because I already have the stuff here and it's easier to go ahead and show you how to graph. So what we're going to do is we're actually going to do E2, which is how to graph this piecewise function. Then we'll go back and do a P1 and a P2 with a different function I give you. So again, a little bit unorthodox. We're not doing E1, P1, and E2, P2. We're going to do E1 and E2 at the same time, and then we'll do a P1 and a P2 using a different piecewise function, okay? So what we're going to do now is I'm going to erase this, and now instead of evaluate the function, right, so for our P2, right, for P2, or sorry, E2, my bad. Come on, brain, I just said it. We're going to graph it. So let's walk through how we graph it. And the reason I didn't just write a set of notes on how to do it is because it's a lot of notes and it wouldn't make very much sense until I actually show you how to do it, okay? So here's what you're going to do. 1, you're going to make a table for each function rule using x's in its domain. 2, you're going to include the breakpoints on both tables. I'm going to just use the word touch, right? So what I mean by that is I'm going to include 3 on both table 1 and table 2 because 3 occurs, right? but I'm going to label my breakpoints as open. That's for if it's not equal to, or closed. And that's if it's equal to. All right, so, and then we're going to graph each piece, okay? So after we do that, we're going to graph each table on the same axes. Now, what's crazy about this is you could genuinely do this problem with two friends, where each one of you graphs a different piece on the same piece of paper. Like, you could graph part 1, and then your best friend could graph part 2, and then your other friend could graph part 3, and just pass the paper along as you go, and it's going to be the same thing as if you did it all by yourself. So here's what I'm talking about. I'm going to start with table 1, okay? So, function rule 1, okay? I see that it goes from 0 to 3, and I know that I'm supposed to include both 0 and 3 on my table. So you could do 0, 1, 2, 3 if you want. Honestly, you could just put a couple points. It doesn't matter. And I know that my y value is going to be x plus 2, okay? I see that there's an equal to next to the 0, so it's a closed dot, and there's a not equal to next to the 3, so it's open, okay? When I plug in my values, 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4, and 3 plus 4 is 5, okay? Then I'm going to go ahead and make function rule 2, right? Function rule 2 starts at 3 and ends at 6. It's always a 5, so how much work you want to put into this is kind of up to you. If you want to do 3, 4, 5, and 6, you could. The y value is literally always a 5. I noticed that 3 is a closed circle, and that 6 is open because it doesn't have the equal to. All the dots in the middle are closed dots by default, right? It's only the endpoints that we make big, obnoxious, closed, and open circles. And if I make a table for function rule 3, sorry, that was y equals 5. I make an x, and this is my x, negative x plus 7, right? And I just need to pick a couple values. So let's just do 6, 7, and 8. That's more than enough, right? And when I notice the 6 should be closed, right? And I know that there's going to be an arrow at the end because this goes on forever. So I'm going to get a 1 and a 0 and a negative 1. Okay, so now I'm going to go ahead and graph all of these. So when I go to graph them, I should look and see what my biggest and smallest y and x values are. Seems like I need x values going up to close to 10, right? So from like 0 to 8, right, is pretty big. And then my y values go up as high as 5 and then down as low as negative 1. So when I pick my window, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 1, 2, 3. Great. Okay, that should be plenty. So now let's plot each one of these, and I would do them all in different colors if I could, but I probably can't. So what I'm going to do is I'm going to cheat and do this one in purple, because if these two are different or the same color, it won't matter because you'll see that they're separate anyway. So I'm going to put a closed dot at 0, 2, and then 1, 3 gets a dot, and 2, 4 gets a dot, and 3, 5 gets an open circle. Okay, so this right here is the entirety of function rule 1. But an interesting thing happens with function rule 2, because 3, 5 was an open circle, but now it's going to get filled by function rule 2, because it turns out that they run into each other. So 3, 5, 4, 5, 5, 5, 6, 5 is going to be an open circle. So 6, 5 is a big open circle. That's my function rule 2. And then the third rule is going to start at 6, 1, 7, 0. So that was a closed dot. 7, 0. 8, negative 1, and it's going to go forever, so that's my function rule 3. And that's what my piecewise function is going to look like. It's 3 distinct pieces. It's not a shock that it's 3 distinct pieces, because the function has 3 distinct rules, different things at different times. Chemistry, then African American history, and then whatever I put third, maybe English, I don't remember. So anyway, 3 different rules. So now what we're going to do is I'm going to give you a different piecewise function, and we're going to do a P1 and a P2, where I ask you to first evaluate the function, and then I ask you to graph the function. Again, your graphing by hand skills don't have to be awesome, right? It should be correct, but it doesn't have to be the prettiest thing I've ever seen. You're not really going to graph much by hand in your life as an adult, I promise. Okay, cool. So let me give you a function that's g of x, and we're going to do all that same stuff with g of x. All right, so let's do, so this is going to be our P1, and that's going to be evaluating, right? And our P2 is going to be graphing. Okay, and in both cases, we're going to use the same function. So the function we're going to use is g of x equals, let's do, oh, I'm also going to just trap you a little and maybe use the parenthetical notation this time for the domain. Yeah, we'll see. Maybe I will. We'll see. Maybe that'll be the next example. Let's do x squared for x values from -2 to 1. Let's do 3 from, actually let's put that there, from 1 to, let's do 4. And let's do, oh sorry, I missed a thing. Let's do x minus 1 for x values greater than or equal to 4. Okay, cool. So I gave you a bunch of values. Okay, so first thing we're gonna do for P1, right? So for P1, I want you to evaluate a bunch of stuff. So P1A, I want g of -2. B, I want g of 0. C, I want g of 1. D, I want g of 2. E, I want g of 3. F, I want g of 4. And G, yeah, squeeze in a G. For G, I want g of, let's say, 8. Cool. Okay, so you're going to take a minute and evaluate this. Pause me, evaluate those 7 places, and then we'll go over it, and then we're going to graph it after. Okay, so again, the first thing you have to do, it's like walking into school late and needing to figure out what class you're supposed to be in, right? You look at the time first. So if the time is -2, which of these windows includes -2? Well, it's going to be the first one, right? So I'm going to use function, again, it helps sometimes to number them. You don't have to, but I'm going to number function rule 1, 2, and 3. So I'm going to start with -2, and I'm going to say, oh, that's function rule 1. You don't have to write that over there, but it's helpful so that you know what you're doing. So I'm going to get a -2 quantity squared, which I realize is a +4. Right? I look at 0 and realize that 0 also falls in the window from -2 to 1. So I'm using function rule 1, which is going to be 0 squared, or just 0. Right? When I get to 1, I'm still using function rule 1 because 1 has the equal to. So even though 1 appears in both rules, I want the one with the equal to. So I'm going to get 1 squared, which is 1. So all 3 of those use the first rule. When I get to g of 2, I look and say, well, 2 lands squarely in between 1 and 4. So now I'm using function rule 2. Well, function rule 2 just says it's 3. There's nowhere to plug in. It's just 3. And I notice that 3 also lives in that same window, so the answer is 3. But when I get to 4, right, so I had a 3 and another 3. When I get to 4, 4 now falls in the last window. I'm using function rule 3 for that because 4 is greater than or equal to 4. So that's going to be a 3, it's going to be a 3 also because it's a 4 minus 1. Sorry, I was going to say 3 minus 1, and that's not what I meant. All right, so it's also a 3. And then when I get to 8, 8 is also in that window, so I'm going to get an 8 minus 1, which is 7. Okay, so that's evaluating this function. Now what we're going to do next is we're going to graph it, right? So P2 is going to be to graph it. I'm going to make a table for each one of these functions. That table doesn't have to be like a detailed visual thing. Like for instance, you might not make a table for the second one. You might be like, cool, I get it. It's a horizontal line at y equals 3. Up to you, right? So when I go to make my table, so let's make my table. So when I make my table for function 1, right? I notice, so if I asked you to identify the breakpoints here, right? The breakpoints that need to show up on your table are 1 and 4. You could also make an argument for -2. It's not really a breakpoint, but it is a place that one of those functions starts, right? So function 1 starts at -2 and goes to 1. So on my table, I'm going to put the -2. It has an equal to, so I'm going to go ahead and note that it's closed. -2, -1, 0, 1. And I notice that the 1 also has an equal to, so it's also going to be a closed dot. Again, any dots in the middle are automatically closed dots. Every graph on every part of a curve on a graph is a closed dot unless you specify that it's open. But at these endpoints, we want to be really obvious about it and be like, hey, this is a big obnoxious closed dot or a big obnoxious open dot. For function 2, right, for function 2, I know that I'm supposed to start at 1 and go to 4. I have to include 1 and 4 even though they're both open. So I start at 1, 2, 3, 4. Both of these are going to be open circles on the graph because neither of them says equal to, right? And then for my function 3, which I think you guys can see if I don't have to move the board too much, for my function 3, which is x, and this is x minus 1, I'm going to start at 4. I see that it's got an equal to, so it's closed. And because it goes on forever, I'm just going to pick a couple values, so 5 and 6. That should be fine. Okay, so when I plug in my numbers, right, negative 2 squared is a positive 4, negative 1 squared is a 1, 0 squared 0, 1 squared is 1. Great. These are all 3's because it's a constant. Literally, it just says 3. And then for the last one, 4 minus 1 is going to give me a 3, 5 minus 1 gives me a 4, and 6 minus 1 gives me a 5, right? So now when I go to graph this, I look and see that I need to go as far back as x is negative 2 and up as far as x is 6. My y values seem to go from 0 to 5, and that's it. So I just want to make sure that I pick a window. 2, 3, 4, 5 is bigger, and there's 6. 1, 2, 3, 4, 5 is bigger, there's 6. Okay, I want to pick a window where I can see the whole graph. So again, I'm going to do the middle function in purple just to show that there are different functions because I only conveniently have 2 colors of marker that are working, not 3. So I go ahead and plug in that negative 2 squared is a 4, right? And I see that that's a closed circle, right? Sorry, computer zonked again. All right. Negative 1, 1, 0, 0, and then 1, 1 is also closed. So I get this little chunk of a parabola, right? So that's function rule 1, that whole little curve. Function rule 2 starts at 1, 3 and has an open circle, right? And then it's just going to stay at 3 until I get to 4. So that's 1, 2, 3, 4, 3 also has an open circle. So it's going to look like this. My function rule 2 is just going to be a horizontal line in the middle of nowhere, right? And then function rule 3 is going to pick up at 4, 3. Well, that's convenient. That kind of fills the hole, right? 4, 3. And then 5, 4. And 6, 5. And it's going to go on forever because it just said that x was greater than or equal to 4, so that's my function rule 3. So sometimes your curves are going to run into each other like they did here. Sometimes they're not going to run into each other. When we get to calculus, it's going to matter a lot to us when these kind of things happen, and we're going to spend a lot of time talking about them, okay? Just as a side note, I don't necessarily think it's worth us doing a separate example of this, but I just want to show you something. I could have, instead of writing the domain restrictions the way I did, I could have written this as bracket negative 2, 1 bracket, this as 1, 4, right? And this as 4 to infinity, right? So this is the other way. So this stuff means the same as this. And so I'm not going to give you a whole other example for that purpose, but I just want to point out that your domain restrictions can be written parenthetically, and that's totally okay. Cool. So we are gonna... Yeah, so what we're going to do before we leave piecewise functions is we're going to try and go in the reverse order and see how it goes. What we're going to do in our E3 is I'm going to give you a graph of a piecewise function, and we're going to walk through how to write the equations for that piecewise function. And so we're going to have to write both the function rules and the domain restrictions. So in example 3, I'm going to ask us to write the piecewise function. Okay, so we're going to write the piecewise function that goes with this graph. And I'm not going to make it super duper tricky. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 1, 2. Okay, so I'm going to go ahead and make us a piecewise function. So let's do... Okay, cool. And I did my best to try and get it to hit actual spots. Okay, so the first thing I need to do when I go to write this piecewise function is I need to figure out where the changes happen and how many functions I have. So I definitely have one function right here. I have one function right here in the middle, and I have one function right here till the end, right? Like this goes this way, okay? So first thing I know is I should have 3 functions. So when I go to write this thing that I'm going to just call f of x, right? And I say, okay, cool, I've got 1, 2, 3 functions. And they're not always going to have 3 functions. I know every picture I've given you so far has had 3 functions. They're not all going to have 3 functions. Frequently, they only have 2. But I just want to walk you through. I figure more difficult is better than less difficult when we're trying to learn a topic so we can handle the harder stuff. So first thing I need is a function rule, right? I'm going to have to figure out the function rules. And then the other thing I need is the domain restrictions. Well, it seems to me that this one starts at negative infinity, because that arrow, right, and goes up until x is 0 but doesn't include 0. Now, if you don't like this notation, the other way to write this notation is to say x is strictly less than 0, right? The next one seems to start at 0, right, and go until 2. Now, because they run into each other, you just need to pick one rule to include x equals 2. Doesn't matter which one you pick. So I'm going to pick this one. You don't have to, but whichever one you pick to include 2, the other one can't include 2, okay? So I'm going to pick 2. The other way to write that would be 0 is less than or equal to x is less than or equal to 2, right? And then for this one, I'm going to say 2 to infinity, but the other way to write that would be x is greater than 2. Again, it doesn't matter which one of these has the equal to, right? But only one does. Right? Only one has the equal, right? Now, why did it matter? Why doesn't it matter here, but it mattered in the first one? Well, in the first one, it was very clear which circle was open and which one was closed. But what's not clear here is that this is some sort of an open circle that is also closed by the other dot. So we don't know which one of these has the closed dot, and it doesn't matter because you're writing me a version of this. There are 2 correct answers. Okay, so then what we need to do is we need to figure out the function rules for these 3 things, right? And that's probably the harder part. So the thing is that all of these are linear, right? So the first one I notice is this 2. 2 is just literally always the number 3, right? It's a horizontal line at y equals 3. That's it, right? So 2 is just a 3. For these 2, for 1 and 3, I'm going to have to go back into that writing equation of align stuff. So I notice, so let's make some notes about number 1. I notice that number 1 has a y-intercept at y equals 2. Right? Now, sure, it's an open dot, but it's still, that's the dot. It's at 2. And I also noticed that I could figure out its slope by doing the rise over the run. If I count this, right, from this dot to this dot, I'm going up to right 2, seems to be 2 over 2, so the slope is 1. Well, that tells me that rule number 1, I can either write it in point slope or in slope intercept. I'll be honest, if something's already handed to me in slope-intercept, I'm probably just going to go ahead and use it. And in this case, this is pretty much handed to you in slope-intercept, right? It's 1x plus 2 or just x plus 2, right? So this is an x plus 2, right? And then for the last one's a little harder because you can see that I can't see the y-intercept. So for 3, the y-intercept is not visible. So I'm going to suggest that you use point slope. Now, I'm always a fan of point slope. Like I said, the only reason I used slope intercept in the first one is because I was literally handed the y-intercept, and why not? So here, I noticed that the slope is down 3, right 1, right? So down 3, right 1, right? So it seems to be that my slope is a negative 3, and I can visually see that the point 2, 3 is on this thing, right? I could have used, so I could use 2, 3, or I could use 3, 0, right? Either of those are fine, right? And so what I'm going to do is I'm going to say, oh, y minus the y value equals my m, x minus the x value. And this is that perfect case where I told you that you don't always have to solve for y, but if you do, you should just add the 3 over. So I get y equals negative 3 times the quantity x minus 2 plus a 3. Now, do you have to leave it that way? No. But I'm going to leave it that way because why would I risk doing something silly and get it wrong? Now, it would totally be okay if you decided to distribute and get negative 3x. That'll be plus a 6, plus a 3, so that's plus 9. That's also okay for that last rule. But my point is that the less math you do, the fewer mistakes you are likely to make. And so this is the answer I would give. So if I were giving this answer, it would look like this because I prefer parenthetical and I prefer point slope. Again, the only reason I didn't do point slope for 1 is because it was very obvious what the y-intercept value was. Okay, so we're going to do a P3 that's like this, and then we're going to call it on this video, which has already been a very long video. And then moving forward after this, we'll start doing some of the other special functions. All right, so let me give you a P3. Again, same task. You're going to write the function that goes with it, right? So for P3, like E3, you're going to write the function that goes with the graph I'm going to give you. All right, so let's do okay, so this dot is supposed to be here, and this dot is supposed to be here. I'm only mentioning that because my graphing skills are terrible. Okay, cool. So you're going to go ahead and write the piecewise function that goes with this, all right? I'm going to go ahead and start, so you can pause me if you don't want me to do it. So rule 1, rule 2, rule 3, right? So I know, and I'm just going to call this one f of x also. I could have called it g of x, but that's fine. All right, so I have 3 rules, 1, 2, and 3, and I need some domain restrictions to go with them, right? So I see that rule 1 starts at negative infinity and goes until negative 1. The other way to write this, if you prefer, is x is less than negative 1, right? Don't do both, pick one, it's fine. Rule 2 seems to start at 1 with a closed dot and go until 2. Now, I'm going to include the 2, so at this spot, again, it doesn't matter, pick rule 2 or 3 to include x equals 2. Doesn't matter which one you pick, I'm going to pick this one, okay? So the other way to write that would be 1 is less than or equal to x is less than or equal to 2, right? And then for the last one, I'm going to have from 2 to infinity. The other way to write that is x is greater than 2, right? Now I need my rules. Well, rule 1 seems to just be when y is 2, right? So that's just a horizontal line when y is 2. Great, congratulations, that's wonderful, right? So that's rule 1. Rule 2 is another situation where I can visually see with my eyeballs both the slope and the y-intercept. So for rule 2, it seems to me that the y-intercept, b, is 0, and the slope seems to be down 1, right 1, right? Down 1, right 1, which is negative 1. So it makes the most sense to me to just go ahead and say that y equals negative x for rule 2. Again, you want to use what's handed to you. If you want to sound fancy and you use your eyeballs to figure something out, you can say by visual inspection, right? All right, now 3 is going to be the hard one, right? So 3 has 2 points that I can see. 3 has this point, which is 2 comma negative 2, and it also has this point, which seems to be 3 comma 2, right? Doesn't matter to me which one you use. You can either count the slope by actual counting, right? Up 1, 2, 3, 4, right 1, right? So I can either count the slope by doing rise over run and realizing that it is 4 over 1, right? Or I can find the slope between the 2 points. It's going to come out the same. It's still going to be a 4 over 1, right? And then I pick a point, right? I'm going to pick the one that doesn't have a negative because I find people are more likely to do stupid stuff wrong with negatives. So I'm going to say that's y minus the y value equals my m, x minus the x value, and then I'm just going to add the 2 over, right, because I need to solve for y. So I don't even have to distribute, so I'm just going to leave my answer as 4 times x minus 3, all plus a 2. Now, if you wanted to distribute, you get 4x minus 12 plus 2, which would be 4x minus 10. That's also fine. You could have used the other point. That's also fine. This is the answer that I would have given, okay? So that's going to be our video on piecewise functions. We're going to pick up in the next video with some of the other special functions.